If making six figures is one of your dreams, you gotta first solve count sorted vowel strings. All right. So you're given an integer n. Return the number of strings of length n that consist only of vowels a, e, I, o, and u, okay, and are lexicographically sorted. A string s is lexicographically sorted if for all valid I, s of I is the same as or comes before s of I plus 1 in the alphabet. Okay, so we want to return the number of strings of length n that only consist of vowels, and the strings created are sorted in terms of the placement. So A has to come before E has to come before I has to come before O has to come before U, right? So it's a sorted string, right? For example, this string would be valid, A, if N was 3, for example, or A, E, O. But UAO would not be valid because U comes before A, right? And this has to be sorted, right? So if you see a U, it has to come after A, E, I, or O. If you see an I, it has to come after an A and an E, right? Just essentially a sorted string. That idea should make sense to you. It should be pretty intuitive what that means. Okay, so it's a pretty simple problem, and it's a pretty straightforward prompt. This is definitely one of those problems that can be misleading because of the constraint. The constraint states that n is going to be less than or equal to 50. So that's, 10 to the 1 times 5. That's a very small, tight constraint on the value of n. So that may lead you to believe that the optimal solution is extremely inefficient, right? Because usually when you're dealing with Leetcode problems, if the constraint is so tightly bound that the value of your input is small, then that's typically the case where the solution is like NP hard and there's no polynomial time algorithm to solve that mofo efficiently, so they have to make that constraint small just so that it doesn't, take all time existing in the universe plus 10 to the billion in order for that algorithm to complete, right? But that's not the case in this problem. So be conscious of the fact that even if the constraint is tight, you may be misled into believing that the optimal solution is inefficient. There could be a really efficient solution, even though the constraint is tight. Most of the time, it's a really good indicator to determine if a problem has an efficient solution, but just be conscious of the fact that is not as always the case. I'm sorry about rambling. Let's go ahead and try to figure out the solution. So for n equals 1, pretty simple, right? Because if n equals 1, don't look at that, you only have really 5 things that you could choose, right? If n equals 1, I can choose an A, and then I'm done because I can't use another character because there's only one letter length string. I can use an A, I can use an E, I can use an I, I can use an O, or I can use a U, right? And there's really, if I thought about the number of ways that I could use an A, well, there's just one way of doing that. There's one way of using an E. This is one way, this is one way, this is one way. And if I add up the total number of ways, 1, 2, 3, 4, 5, I get 5 sorted strings that consist of vowels only. Okay? Maybe 2 will reveal something a little bit more helpful. Well, if I use A as the first character, the next character I can use is E. Right? I could use E. Well, I could do that too. I could use the next character as A, right? But I could also use the next character as E. I could also use the next character I. Could also use the next character O. And I could also use the next character U, right? Because I can only use these 5 letters. But since I'm starting with A, and it has to be lexicographically sorted, I have freedom to use any subsequent letter, because any subsequent letter would meet the constraint such that it's lexicographically sorted. Okay? Now I'm going to color this just so that it's clear what I'm doing, because this is going to get a little bit cluttered. Okay? Now for E, this is where we start thinking about the nature of being lexicographically sorted. If I wanted to use E as my first letter, well, I can't use A as the next letter because it has to be lexicographically sorted. So in order for it to be lexicographically sorted, the next letter has to either be E or a letter in the alphabet that comes after E. So it could be E, or it could be I, it could be O, it could be U. And then we play this same game with I and O and U. Right? For I, the next letter could be I, could be O, could be U. For O, could be O, or it could be U. And then for U, we'll just use black, I guess. For U, the only next thing could be U. So this kind of articulates all the next options you have for n equals 2, right? For the first character, I could use A, and for the next character, for the first character, I could use any of these. For the next character, I could use any of these. But the links between capture or articulate the connectivity that could occur, right? So if I was to look at any path, it would give me one of the valid strings, right? That's the idea. Like from E, I can go to EE, right? And that's a valid string. I could go from E to O, and that's a valid string. I could go from E to U, right? That's a valid string. I could go from O to U. That's a valid string, right? We're going to capture, if we've captured all of these paths, we would capture all possible strings that are valid, right? And you'll notice that there's no invalid string within these boundaries because, you know, first we thought about the letters that we could use, and then we created edges to ensure that within with the letters that we could use, we never attach letters that can't be attached in the order of which they're set up, right? So E would never attach to A because there's no link from E to A, right? There's a link from A to E because that's valid, but a link from E to A does not exist because that is not lexicographically sorted. Okay, and you'll notice here, there's 15 in this case. So how does that work? Well, I guess this leads to a natural dynamic programming solution because, well, first we're dealing with a DAG here, which is the directed acyclic graph. If you're not familiar with, you know, algorithm theory, that may be a little bit of a foreign term, but essentially what that means is there's a way to build this system where we think about we think about a recurrence relationship. We think about adding something in terms of what it can be added to, okay? So when I think of A in terms of what it can be added to, I look at this graph and I say, what can A be added to and how many ways can I do that, right? So the number of ways, we're going to call this N of U at N. And what I'm basically saying with this weird system I just created is this is going to represent, or this is going to be used for our catch, our recurrence relationship. This is the number of ways to create a n length string ending with a U. Now, this is U as in the node U, not U as in the letter U. So maybe we should give it a different letter. So let's call this X, okay, with a X letter. So basically what this means is how many ways can I build a string that ends with the letter X, which could be A, E, I, or U, such that it's of length N, okay? So in this example, how many ways can you draw a letter A ending with an A that's only length 1? Well, that would be 1, right? The number of ways to create a 1 length string ending with a is what? It's 1, because it's A itself. Same with E, same with I, same with O, same with U. How about A? Well, in this case, well, how many ways can I create a string that ends with A? Well, either it's based off what goes into A. Well, what goes into A? It's just this length here. So this would be 2. Or, this would be 1 as well, right? Corresponding to AA. Well, how about E? Well, E could attach itself to A, so that'd be AE, or E could attach itself to this E, so that'd be EE, so this would be 2. How about I? I could attach itself to this A, right, because I'm just dealing with the links that go into it. So it could attach itself to this A and become AI, or EI, or II, so this could become AI, EI, or II, so this becomes 3. And then you'll just kind of notice where we're going with this pretty clearly, right? This becomes 4 and 5, right? Because O can attach itself to A, O, E, O, I, O, 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 U, O, O, that's it. And then U could be A, U, E, U, I, U, O, U, 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 me, you, me, so that could be 5. So that'll give you the total number of, things that we could connect. And you'll notice if we were to extend the system out, right, we could continue this process. And at the end, what we have is we just sum this up, and that'll give you the total number of solutions, right? Because the total number of ways we can do this is the total number of ways that we can make an end-length string is the total number of ways that we can create an end-length string ending in U, plus the total number of ways of creating an end-length string ending in O, ending in I, ending in E, ending in A. So if we sum these up, we should get the solution, which is 5 plus 5 plus 5, which is 15. And then just for the sake of making this a little bit clearer, let's make this n equals 3, which would correspond to adding another one of these systems. Let's first clean it up a little bit before we add it. So if we made this n equals 3, it would be the same edges, right? Because if the previous thing ends in E, now we know that's the number of valid strings ending in E. So then we have the same links, because now that it ends in E, the subsequent things have to be E or have to come after E. Yeah. Whoa. All right, so let's link these up again like that. So then how would we work with n equals 3? Well, for A, there's one way to get to A, and there's one way to get to that previous A, so this would still be 1. Now here's where it gets a little bit more interesting, because there's one way to get A, and E. So if E attaches itself to A, there's one way to get there, so we'd get 1 there. But if E attaches itself to E, well, there's 2 ways to get to this E. So that means there's 2 additional ways that we could get to this E, right? The idea is basically, if this had AE and EE, right, there's 2 ways to get to this E. So we can attach this E to these 2 previous solutions to get AEE and EEE, right? So that's the basic idea. So I just sum up the total number of ways I can get to the things that I can connect to before me, right? So this would be 2 plus 1 equals 3. Now for I can attach itself to A or E or I. There's 1 way to get to A, there's 2 ways to get to E, there's 3 ways to get to this. So this is 1 plus 2 plus 3 equals 6. And O can attach itself to A or E or I or O. So that's 1 plus 2 plus 3 plus 4. So that's 1 plus 2 plus 3 plus 4, which is 10, right? 4, 3, 7, 10. Okay. All right. And then U can attach itself to 5, to 4, to this, to this, to this. So that's 1 plus 2, 3 plus 3, 6 plus 4 is 10 plus 5 is 15. Like so. And you can notice that this problem will just keep propagating forward, right? So the recurrence relationship then is, well, the number of ways to get to a node X using n characters is just the sum of the nodes Y, such that Y is less than or equal to X, right? Because to attach to a node, right, to attach to this node, I can only attach things that are less than or equal to it, right? I can attach I, E, or A because it's less than or equal to I, right? To attach an E, I can only attach things that are less than or equal to it. So that's E or A, right? So I can only attach Y's to X such that the Y's are less than the X. And I'm going to look at all nodes Y. I'm going to sum up their values using something that's one less in terms of the length of the string, right? All the length 3 strings I can create ending in I, right? So an example would be this I here. Right, so this I is length 3, right? And I can attach this I or this E or this A. So in terms of the relationship, that'd be N of I using length 3 equals the sum of nodes Y less than I of length 2. This is an I here. Or no, this would be a Y of length 2, right? Because that equals N of A of length 2 plus N of B, N of E length 2, sorry, plus N of I length 2. Right, I'm basically adding up these links. This link, and this link, and this link. Okay, so this basic recurrence relationship will get us to the solution. So let's go ahead and write that, and then we'll think about some further optimizations that we can create. Okay, so well, we'll just do it with a default dict. So we'll create n with a default dict where the default value is 1 to represent to represent what? To represent our values, I guess, because that'll be the default value. So we'll look at each n value in the range 1 to n plus 1, right? Now, A and E. So we should probably start. Trying to think about the best way of doing this, because I know a much faster solution where you don't even need to think about this. So it's kind of hard to be like thinking about it in terms of something that's not even optimal. But okay, so we'll go from 1 to n plus 1. Actually, we'll start at 2. We'll go all the way to n. All right, that's fine. And then we'll say, okay, we'll look at each letter. We'll call it X. Why did I capitalize it? For X in range 1 to 5. Or no, to 5. Right, because there's 5 vowels. There's A, E, I, O, and U. So we'll just capture all those vowels by using numbers. We'll say, okay, N of this letter using of length n equals the sum of n of each letter y using one less length. So I'm just converting this sum, right? So n of x of n equals the sum of all y's less than or equal to x using one less letter for all y's that are less than or equal to n. So that'd be from 0 to y plus 1. All right, and then at the end, we just return the sum of each n of length n for x in range 0 to 5, right? Because that'll get us all vowels. Int object is not subscriptable. Oh, because this is a dictionary, sorry. So all these things need to be like this to represent that we're using a dictionary, not a linked list, or a list. Okay. Y is not defined. Oh, oops. And x plus 1, because x is the current node that we're looking at. Not a good sign. All right, cool. So this solution works. It looks pretty quick. Technically, your solutions are going to be wild and all over the place, right? Because your end value is so small. So you might get like one submission that's better than 99%, and the next submission is better than 4%, right? I wouldn't really trust whatever that runtime timer, space checker, whatever determines, right? What that auto grader determines, because there's going to be a huge variance because your constraint is so tightly bound. So how do we make this just a little bit more efficient? Well, I guess the first thing is we're only basing the current thing on the previous thing. So we don't need to keep track of things that are 2 iterations before, right? We only need to keep track of what's occurring right now. And what you'll also notice is that there's a running sum, right? So let's first make that that primary fix, which is, we don't need to update everything. We can just keep track of the last iteration, right? Because the idea is regardless of how large the system is, this iteration is only based on the previous iteration. So we only need to keep track of like 2 things. When we're looking at this iteration, the values here no longer matter, right? The stuff that happens on this column is no longer relevant. So we don't need to keep track of that. So to save space, we just need to keep track of the previous thing that occurred, right? 1, 2, 3, 4, 5. And then that means that we can create a new array. This would still be 1. Sorry, I'm trying to think about how this is going to work. So then we go through we go through each index, and we'd say, okay, dd at x now equals the sum of dd at y for y in range x plus 1, right? So we only need to keep track of the previous iteration, and then at the end, we just reset d equal to dd. And then at the end, we just have to return the sum of d, because that will give us the sum of all the values, right? So now we're basically just keeping track of the previous iteration's value, right? So if we print, we don't need to do that. Hopefully that makes sense, right? So now I'm just keeping track of the previous iteration's value for each of the vowels and then shifting it each time, right? So I set this equal to D. I find out what DD is, and then I set D here. So on the next iteration, when D is here, I can look at DD here. So I can just shift over every time. So that's essentially what I'm doing, right? I use this as D, I find out what the next iteration of D will be, and then I set that as D, and then I find the next iteration of D and set that as D, and so on and so forth. Okay? Now technically this is there's a constant solution, which we're not going to cover because it's more of a statistics-based solution, but this is as good as the dynamic programming approach will get in terms of runtime and space complexity. But you could technically do a small optimization to make it a little bit faster, to think about the fact that, one thing you'll notice here, right, is like, this is 1, and this is 2 plus 1, and this is 1 plus 2 plus 3. This is 1 plus 2, and this is 1 plus 2 plus 3, and this is 1 plus 2 plus 3 plus 4, and this is 1 plus 2 plus 3 plus 4 plus 5. So essentially, because the way that this works is everything's just based on itself and everything that comes before it, there's this running sum idea, right? This is 1, and this is just one new thing added to it, which is itself, right? And this is 1 plus 2, which is this part. And then we have a new value 3 that's added to it. So it's just yourself plus the previous thing, right? What is O? Well, the value at O, this is an O here, is 1 plus 2 plus 3 plus 4. I'm talking about within this context here. Okay, what's the value of I? The value of I is 1 plus 2 plus 3. And what was the value of O before? It was 4. So the weird thing here, you'll notice as well, D of O equals D of I plus what D of O was before. I'm using D now when I should be using N. But the idea is you become what you were before plus whatever was previously added, right? This is, what is D of U? D of U was 5, and then it becomes 1 plus 2 plus 3 plus 4 plus 5. Well, that's just D of O plus D of U, right? D of U equals 1 plus 2 plus 3 plus 4 plus 5. It used to be just 5, so it's really just 1 plus 2 plus 3 plus 4 plus 5, right? So you don't really need even this DD idea. All you have to say is, well, for I in range 1 to 5, D of I equals whatever it was before plus whatever we populated before it. And then notice it's slower, but again, you're going to have huge variance because your N value is small. This is technically an optimization, right? And you could move this, right? If you really wanted to be fancy with it, you don't even need this value anymore. You just need to make sure you do this process that many times. So we could do a product, and we can move this all onto three lines, like so. Now I'm wondering if I want to think about the constant time algorithm, but I don't want to push my luck. So we'll just stop it here and talk about what this is. Well, let's say that N, okay, we already have N given. So time complexity, we have to look at all N variables, right? I mean, we have to look at all N length strings from 1 to N. And then we do 5 operations where we update this thing. So for all N variables, we look at 5 things and we update them accordingly. So we look at a constant number of things and we do a constant number of operations. So for all N things, we do a constant number of things, which include constant operations. So it's a constant times N, which is just N. And then we return the sum of N, D, but that's just those 5 variables that we populated. So it's O of N runtime. In terms of space, regardless of the length of the string that we're creating, if it's length 5 or length 1,000, we're only going to update it. We're only going to create space for the 5 values that we're populating. So regardless of the size of N, we only have to store information about 5 things. So that's O of 1 space. All right, guys. Hope you have a good rest of your day. Peace out.